nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
We'll be reviewing what we have learned very briefly. I have just picked up a few slides from before that summarizes or that highlights the important problems from before, and also probably a personal perspective that what I see ahead going forward. Now, let me begin by a quick review of what we have learned. We have learned many things, but the essence of what we have learned is not really too many. I'll talk about that. Going forward, many of the things that we have learned, the principles will remain the same. The MOSFET, the bipolar, the diodes, quantum mechanics, statistical mechanics, the basic things are not going to change. But as we go for new devices, how we apply them, apply the basic concepts, that probably requires a good understanding of what we have learned. And finally, I'll conclude. Now, if you remember, in the beginning of the semester, when I introduced 606, I said that, that we learned something about the foundation of physics, which is on quantum mechanics and statistical mechanics, and they will lead to the transport equation, the drift diffusion equation, the thermionic emission equation, and all those. And that would lead to a understanding of resistors, where sometimes you have seen we have shine light on it, we have put various boundary conditions and applied battery across it. We have done all sorts of things, and we have talked about diode, minority carrier transport, bipolar junction transistor, various non-linearity or non-ideal effects associated with it. And finally, for last 10 lectures or so, we had been talking about MOSFET and MOS capacitors. And I said what we didn't discuss, or would be discussing in this course, are that eventual applications of these devices in variety of configurations. For example, laser is just a diode, but we didn't discuss it, but essentially it's just a diode. Thin film transistor, I will talk a little bit about that today. It's a MOSFET. It's a pure simple MOSFET. If somebody says I have a thin film circuit, you shouldn't be worried. You should just say, okay, I know this is a MOSFET. I will have to just do the square law, the channel length dependence, and everything is exactly the same thing. MEMS is exactly again a MOSFET. MOSFET that has a variable, the gate capacitance is variable. Everything that you have done, in fact, that you can easily do the whole analysis. The MEMS analysis is you can copy essentially line by line from the MOSFET analysis, almost, not everything. So the idea is that although we haven't discussed all the semi-classical devices for various applications, many of them, if you know these three, it's like an alphabet, then you can read or apply for any other. And finally, the circuits and systems, that is of course a combination of all those things together that we haven't discussed, and 606 was this part. So what is it in this part that you should remember in general? Well, the thing that you need to remember is that how we arrived at the transport equation and what were the essential, and the transport equations always are so complicated. Remember, three-dimensional equation, partial differential equation of the diffusion, drift, and all those electron holes going through, that many times you can solve them numerically, no problem. And you have done that, right? You have done that in homework. But many times simplifications are necessary. And what I've tried to do throughout the course to explain the various simplifications that goes with resistors, diode, and bipolars. You have learned about that. So what is it from this quantum mechanics, statistical mechanics to devices that we tried to understand? The thing was that in the beginning, the entire quantum mechanics, idea of the quantum mechanics was encapsulated in the idea of an effective mass. that there were periodic potential. I'll come to that. And when you solve the Schrodinger equation in the periodic potential, we got the band diagram, the EK diagram. And from the EK diagram, we argued that electrons mostly sit near the bottom. And when they sit near the bottom, then the curvature of how they move can be described by something called an effective mass. And that also gave us this idea about this band gap, the separation between conduction and valence band, the highest occupied level and the lowest unoccupied, highest occupied level and lowest unoccupied level. And so those two were from quantum mechanics. What did we learn from statistical mechanics? Well, Fermi function. That's the only thing we got from the statistical mechanics, and that we derived in equilibrium. And we combined these two ideas, the two notions, into this effective parameters. One was this effective density of state. Well, effective density of state looks like density of state, but actually is very different in some way, right? Because remember, effective density of state depends on temperature. So if you change the temperature, there is this kT in 3D, it has T to the power 3/2. Because effective density of state are not the density of state, total density of state, but only the fraction that would be occupied at a given temperature by electrons. So you multiply by the Fermi function and then integrate and effectively put them at the conduction band age or the valence band age. So NC and NV, both of them, they know about band gaps and band structure as well as the Fermi functions. We talked about mobility and the scattering time, which is related to the scattering time. Essentially, that shows any deviation from perfect periodicity that was encapsulated in mobility and scattering time discussion. Okay, once we had that, then there's one other thing that we derived that was very important, was that at any point in the non-equilibrium conditions, under all non-equilibrium conditions, the N multiplied by P is always equal to Ni squared, the intrinsic carrier concentration, and the quasi-Fermi level separation divided by KT, right? This is something we learned. Now, of course, Fn and Fp you have to calculate depending on various situation, but if you know that, you can always find out what N and P is. This is non-equilibrium statistical mechanics in some way, because it happens when Fn and Fp are different from each other. Of course, when they're equal, you get the original relationship. So that is all that we learned from quantum and statistical mechanics. Now, a very quick reminder that how we went there. First of all, we made that argument that electron in a crystal essentially goes through a periodic potential. And do you remember that there are different types of crystals we talked about? In 1D, there is one type. In 2D, there are 5 types, right? 5 types of periodic things. And in 3D, there were 14 Bravais lattices. There were 14 Bravais lattices. And that argument was very important because that allowed us to get the periodic potential. And from that periodic potential, we solved the Schrodinger equation. The age of the Brillouin zone was pi over A being the smallest lattice spacing, and each solution was separated by each other by how much? Pi divided by Na, N being the number of atoms, right? Do you remember that? And so we counted that each band, if you don't include spin, each band has N state. N is the number of atoms that you began the discussion with, and if you include spin, it will be 2N, always even. And remember how that was used to explain the difference between metal and the semiconductor, right? That even states will always remain fully filled. If you have even number of electrons, then it will remain fully filled, so then you can have a semiconductor. If you have odd number of electrons, then one of the bands must be half filled, and that gives you a metal. So you remember all those discussion about how this information was used. And from there, we got the effective density of state, and this is, let's say, like a three-dimensional density of state, which is counting how many places electrons can sit. And depending on whether it's a one-dimensional crystal, 2D or 3D, then you will have different number of states to begin with. What do you think this particular one is? This is a three-dimensional one, because in 1D you'd have a very large density of state in the beginning and then it will go down. 2D it will be flat, and 3D it starts small and then gradually builds up with 3/2 of the energy. That as you go up in the energy, it goes up with 3/2. Okay, so we got that, and eventually we got the effective mass with the second derivative of the energy band diagram. You remember that this is for the conduction band, goes with the green, and for the valence band there was this negative effective mass, but then we had negative charges for the holes, and then that's how we got a positive effective mass for the holes. So that is how we encapsulated the information. Now, the reason I bring it back is to make you aware that this you learned is good. Most of the things you will be encountering, let's say, in the near future, or the things that you would encounter in work, this recipe and everything will be fine. So if you have a new device, you can just go ahead, get what the effective mass is, and solve the problem, no problem. But you have to be careful that all periodic potential need not give rise to an effective mass. That's very important. Anytime you have a new device, you should always examine back that whether your foundations on which you will be doing the calculation, whether your foundation is still okay or not, right? And this is what most of the students don't do, or not, I shouldn't say students, most of the scientists don't do. They see a new device, they bring in the MOSFET, open up the book, look at the MOSFET equation, start from the MOSFET. It's not where you should start. You should always check back whether your band structure and other information which led to MOSFET equations, whether the foundations are still okay or not. That may take 10 minutes. If you satisfy yourself it's okay, then you go ahead and use whatever semi-classical equations you want to use. If it is not, then you take a step back and redo the analysis. So one example is this graphene, the material of graphene, and you have done homework on this, right? Do you remember you did the periodic cell and you had to make that argument that the unit cell, there is a special way you had to define the unit cell. Remember? You did the homework. You also did the homework in which I tried to show you that this is a two-dimensional thing, right? Two-dimensional lattice. So therefore, the corresponding EK diagram will be two-dimensional. One axis will be Kx, another axis will be Ky, and the edges of the Brillouin zone, it will be pi over A and pi over B. Do you remember that? Do you also remember that this is a direct band gap material, but the direct band gap doesn't occur in the gamma point. It occurs near one of the edges. Do you remember? This is the homework you did. And essentially, if you blow it up, you will see that the EK relationship is actually linear. You see that as the energy is going up, this is a cone opening up whose sort of radius, which is the K, is directly proportional to E. There is no parabolic relationship anymore, right? So in this case, you obviously have a density of state. By the way, so the region that you see with the cone-shaped region, which essentially just accounts for the middle of this region where the density of state is flat. This density of state is flat. You knew that, right? In two-dimensional, the density of state is flat anyway, but in this case, if for a constant EK relationship, instead of density of state going up, 3/2 or 1 over square root of E, this is essentially flat. What happens if you go a little bit above that? You can see from the left-hand plot, the band diagram plot, that very close to the conduction and valence band edge, sort of, then it is like a cone, little cone coming up. But if you go up a little bit more, then it's sort of deviating from a pure cone-shaped region, and so therefore the density of state way up in energy and way down in energy will be different, right? In here and here at higher energies will be different. But for very close to this band edge, the density of state is essentially constant. But you also realize that this is not going to work. There is no second derivative. If you try to compute it, you'll be in trouble. And I also told you that when you don't have an effective mass, only thing you care about is the position of the electron, velocity of the electron. For that, to calculate those two quantities, to follow the electrons around where they are, you don't need effective mass. And please review that part of the discussion, because if you know that part, then all devices, all materials will be fine. You either can define effective mass or you cannot. Both cases you can handle the problem. So these would be the two cases to remember. Now about Fermi functions, there are several things we discussed. We looked at the density of state, of course, and from the density of state, we looked into the number of states per energy. So for example, in a three-dimensional crystal, you have at energy U1 fewer states, E2 you have a little bit more, E3 little bit more. Had it been one-dimensional, then the E1 would have a lot more than E2 and E3. So the idea is that once you have the density state, you know where to put electrons. Let's say you have 4 electrons. Now in doing this derivation, the most important assumption, the derivation was simple, right? Just bookkeeping. You see, you want to conserve energy. You make the argument that electron can neither be created or destroyed, right? And every state 1 electron. If you don't account for spin. If you account for spin, you can put 2. So we did a very simple derivation, you know, it's no problem. Algebra was not a problem. But the important point I wanted to make, that this way of doing things only occurs if is only valid if it is the extended crystal, where 2 electrons actually, although they are in the same energy, they are not physically close to each other. Because if they are physically close to each other, there will be strong Coulomb repulsion. And we haven't accounted for that Coulomb repulsion here. Do you remember? And the example I gave, yes, for example, there are 2 students who are not in good terms. One could be in the 2nd floor of electrical engineering, and one could be in the 2nd floor of chemical engineering. They are perfectly happy. They are both in the 2nd floor, 2nd level energy, but they are not physically close to each other, so everything is fine. This is that argument you make when you do this type of derivation of the Fermi function. But I also told you about when you put an electron in a localized state, like a donor and acceptor. In that case, of course, the Fermi function gets modified by this degeneracy factor GD. That accounts for the correlation. Now, this is very important because although, you know, dopant densities and other things that is classically treated, everybody knows, you now know how to handle this. This correlation effect and sort of repulsion effects are very important. For example, this is, for example, a molecule, right? People, have you heard about molecular electronics, right? Where you put, instead of this huge MOSFET, you put one molecule, and this could be a C60, a fullerene molecule, and this is between 2 contacts, 2 metal contacts. So the 2 sides are, these 2 tips are 2 metals. You have one molecule, and the electrons can go from one to another, and the tip-shaped region that is coming up, that could be like a gate. If I give you this problem and ask you to do the band diagram, you should be able to do it. It's a metal, semiconductor metal sort of thing with a gate at one point. But the Fermi function for this, because the electrons are so close to each other, there's no way that they will be far separated. So in this case, you have to worry about Fermi function and apply it properly, right? So that's for that you have to do. So you cannot just simply take in that case, well, I have read in 606 what effective density of state is. Now let me put it in a molecule and start calculating. Well, that will be dangerous. So it's good to, if you see something this different from the things that you have learned in this course, then take a step back and ask yourself that what type of density of state should I put here? What type of Fermi function should I put here? Those things you should think about. By the way, there are lots of papers. People are already working on it. So once you recognize there is a trouble, then if you go in Google or search for papers, you'll find many papers. So it's not a problem. But the thing is to identify that you have a problem. And then there are lots of solutions. So that's something you have to be careful about. Okay, so I have my quantum mechanics, density of state, if a band gap and all, and Fermi function appropriately modified for the particular situation. Then you have the transport equation. First one is the Poisson equation. All the time, Poisson equation to me is the single most important equation, because everything at the end is governed by the Poisson equation. If you do not have good control over the band diagram, then no devices that you make are ever going to work. You know, current comes later. First of all, you must be able to control the current. Then everything else sort of follows. So that's, and we saw graphically how to solve that by band diagram, right? That's the solution of the Poisson equation. And then there were continuity equation. Then this is the drift diffusion equation. Of course, in many cases, we have also applied thermionic emission. What is the difference between thermionic emission and drift diffusion? Well, in one case, scattering is very important, and scattering is hiding in the mobility and in the diffusion coefficient, right? That's where the scattering is sort of encapsulated. If you don't have any scattering, let's say across a hetero barrier, and the electrons going on two sides without scattering, in that case, you cannot use this theory. Then you use thermionic emission theory. Now, many times they will give you the same results if you use it appropriately, but many other times the results could be very different. And so the idea is that this is a complicated equation. There are numerical solutions available, right? You can have Medici, or you saw in nanohub.org, you have a set of tools. Many of them are actually just solving these equations numerically. And I told you about that also, right? How do they do that, solve it numerically? But many times you will actually simplify it and solve it for particular conditions. Now that simplification is generally very powerful. It has been developed over the last 30 years. Very powerful. As a result, for many modern devices also, it's not only for the old, many modern devices, those approximations will still hold, because you are just approximating a differential equation. And so therefore, whether it's a modern device or an old device, doesn't matter, so long you know the basis of the approximation. Right? So quickly reminding you about the band diagram. Now you should be experts of this. I'll be very sad that if students from 606 cannot draw a band diagram 15 years from now. But hopefully that will happen. This is, for example, a diode. Very quick reminder, follow the rules. Flat Fermi level, the bulk region, you put the conduction band, let's say in the N region, with the separation, appropriate separation for the N side, and then put the chi is the work function, and similarly do the same for the P region. The Fermi level to EV separation is dictated by the doping, right? The doping. And then you again put the work function down there, that's the vacuum level. You have to make the vacuum level continuous. You have to make the vacuum level continuous and copy down. You'll have to copy these things down. And whatever you get, that's the answer. You cannot be wrong. So whatever you get, no matter what device it is, at least to 0th order, this is how the device looks like in equilibrium. Why is it in equilibrium? Because flat quasi-Fermi level is a property of the equilibrium. So equilibrium is in fact defined by flat quasi-Fermi level. If you have a non-homogeneity, then of course there will be a gradient. And as soon as you have a gradient, then you have a current flow. And that is not allowed in equilibrium, right? No current flow. Detailed balance. Every electron, every pair of states equally balanced back and forth. And that's different from steady state, where it's balanced on average. Not individual state by state, on average it's balanced. So here in equilibrium, every pair of electrons, you take two electrons from here and here, two states from here and here, they are balanced. Two electrons from the far right side on the band diagram and here, they are balanced. They are balanced in every position in energy, every position in space, they are perfectly balanced at every point. So therefore, this is what how equilibrium is defined. Now, once the equilibrium is defined, I always wanted to emphasize the importance of minority carrier equation. Right? In minority carriers, what you do is you ask the question that if I have a complicated device, where is it the simplest to solve? Anytime you have a drift-based region, which is the majority carrier sides, Drift is always dangerous. Why? Current is small generally. Current, you know, if you have a barrier up and down, going up and down, the net amount of current will always be small. Majority carriers has a lot of electrons, right? 10 to the power 18, let's say. Small current, lot of electrons. So if you say J is Qn mu E, so you can see the electric field will be minuscule. It will be minuscule, right? Because N is very large, J is small, electric field will be minuscule. You make a little bit of mistake in the electric field, your current is off by an order magnitude, let's say, right? Very dangerous. Therefore, the easiest problem always to solve is to go and solve it in the minority carrier side, where the electrons are fewer, and then you can make the calculations much more easy. So here, in order to do the non-equilibrium part, the most important thing is this part, that you sort of slightly out of the edge of this slide, which is to ground one terminal. If you start drawing without grounding, all potentials are relative. All potentials are relative. Whether something is a plus or something is minus, it always depends on where is your reference. So no matter what diagram you draw in on equilibrium, ground or one terminal. You ground one terminal, then all the relative potentials of all the batteries, they will be specified. And once you specify them, then you will shift the quasi-Fermi levels accordingly. And the quasi-Fermi level should always come to the other side of the junction and stop. This is for the low injection condition, that you understand. But in general, this is how you would get started. The important point here are to take care of the boundary conditions in the minority carrier side. I will not go into details, you know that. And correspondingly, in the majority carriers is equal to P naught, and the minority carrier you always get that separation of the quasi-Fermi level, and that's correspondingly equal to the applied voltage VA. So you can calculate how many extra carriers you are injecting at the edge of the P doped region. And on the other side, if it is a metal, then electrons goes out with infinite velocity. So you will set the carrier concentration on the other side to 0. If you have a surface recombination velocity, as was the case in the last exam, then you would set a finite surface recombination velocity. So first look for the two boundary conditions and solve the diffusion equation in here. Is there any recombination in this particular one? No recombination, good, because then this is straight line, slope at every point is the same, that means current is continuous. So that means you are not losing particles, right? So this is how it would work. So understanding minority carrier diffusion and transport is very important, not only for diode, but in general for any types of series connected devices. Many times you will find one region where it's diffusion dominated. You just go there and start solving. Another important one was anytime you have a discontinuity, we talked about thermionic emission, and anytime you have a discontinuity, that's what you should start in the junction region. I'll not go into the details, but just to remind you that the tunneling current is essentially, the total current is essentially equal to the two fluxes, different of the two fluxes. Whichever side is grounded, which side is grounded by the way here? Here, the metal side I have grounded. So whichever side is grounded, you set that quasi-Fermi level the same, and the other quasi-Fermi level you move up with respect to it. And you can then make that argument that from the metal side, it is not changing with the applied voltage, right? Metal to semiconductor side, not changing with the applied voltage. Where from the semiconductor to metal side, yes, of course, the barrier is lower. So the more electrons will flow. Right? The red electrons, there will be, number of red electrons moving from right to left is far easier than compared to the blue ones. Blue ones, the fraction you see above the dotted line that moves from left to right is remains almost the same. And we made this argument that all you have to do is to realize only half the electrons move to the left to right. What happened to the other half? They are going the other direction. You know, it's a random motion of electrons. So only half would go, and not everybody will be able to go, only the ones above the dotted line, because the ones that are below, they will come there, get reflected in the wall, and then potential barrier and go back. And so that takes care of that Q phi b over kT term, and VTH is the thermal velocity, the rate at which electrons are moving. And so you make these arguments about various currents. I'm just reminding you, and once you have done that, you can calculate the net current. So try to go ahead and see whether you understand these arguments. I mean, we have discussed it in great length in the class. Okay, DC, diffusion theory, minority carrier transport, thermionic emission. That's DC characteristics. AC, most of the time you will bias it at a given configuration. Then you will put a small signal. So there is always a battery, that large battery VA, that puts the thing in some DC biasing condition. And then the small wiggle thing that you have, that one, that's V naught sine omega t, that one is sort of from your antenna or wherever you have the small signal coming back and forth. So the DC information is already incorporated in the specific values of the conductance C, junction capacitance Cj, and the diffusion capacitance Cd. This is already included. And the magnitude of the small signal essentially dictates how much current will pass through this. If you have more small signal, more current will go through this. But the DC dictates the magnitude of this various components. So the first thing is Cj, the junction capacitance associated with majority carriers, right? Always majority carriers, the junction capacitance, and majority carriers can respond with dielectric relaxation time very fast, right? They can come in and out very fast. So therefore, for all majority carrier devices, you must have a Cj. If you don't have it, then you are in trouble. So here I made the argument how the electrons and holes come close to the edge of the depletion region in and out as you're changing your AC bias a little bit, and that's how you calculate the junction capacitance. How do you do it for diffusion capacitance? The other one, that once you inject it in the diffusion side and the minority carrier side, depending on how the frequency of your wiggle of the small signal, then there will be a ripple of carriers moving forward. If you are doing it at a very slow speed, then you will have a junction capacitance. If you are doing it so fast that before the electrons can get to the other side, you are asking that come back. If you are sending, then there will be a phase difference of the current that is flowing through and the signal that you are applying. And so there will be a corresponding change in the capacitance. That will be frequency dependent, right? So the diffusion capacitance correspondingly will have a value associated with this minority carrier modulation. Now one thing here, if you don't have minority carrier, you do not have minority carrier diffusion capacitance, of course. Now, do you realize why these things are in parallel? Why aren't they series? So you should ask yourself why they are in parallel. I mean, it looks like they should be in series. You have a junction capacitance, then the diffusion capacitance seems to come after the junction capacitance. Why aren't they in series? So that is something I will ask you to think about. I have answered this, of course, during the lectures, but I will ask you to think about one more time. This is many senior people, they sort of get trips over this very simple notion. Large signal. Large signal is different from small signal. Large signal is different because when you change the signal suddenly, then let's say from 1 to 0, then it doesn't go through slowly through this various equilibrium points to the other side, but rather you sort of give it a sudden impulse of voltages, and then most of the time it will go directly, it will satisfy the current immediately and satisfy the without changing the voltage. The current, whatever current the output circuit wants, the device must give that current immediately. Voltage will come a little bit later. Why? This is because of the capacitance. Because capacitance doesn't allow the voltage to change suddenly. It allows the current to change suddenly. Now think about it. Instead, we didn't have any inductance here, right? There is no inductance. Now that is something to think about. Why didn't we have any inductance in a diode? Shouldn't there be an inductance there? In fact, you can show that carbon nanotube and other more modern devices does have inductance. So in that case, you can have inductance. If you had inductance over there, your current couldn't change also. But for the semi-classical device we are thinking about, the diode, right? In that case, only capacitance, voltage doesn't change, current changes immediately. Okay? And we talked about how their corresponding responses occur and how to calculate the storage time, TS, and the corresponding how it goes back to the other equilibrium time constant, equilibrium current, let's say. So you should think about it because this is sort of very important. And the way we analyze this is this charge control model. Very quickly, I'll just flip through this just to remind you where we had been. We just said that solving a diffusion equation in position and in time is horrible, cannot do it because the partial differential equation will get rid of the spatial variation altogether and only focus on the number. And therefore, we integrated over the space, and therefore, only thing we care about is area under the curve, which is, let's say, area under the rate curve at a particular point, the total number under that, without really bothering about how they are distributed over the whole region. And we correspondingly got equations. These are the charge control equations, and you know how to solve now charge control equations, hopefully. Not all of you could do that very easily in the second exam, but in the final exam, I'm sure by that time, it will be crystal clear to you, hopefully. But the thing is that look at this equation. This is almost like if you had a RC circuit with a voltage in the beginning. If a second year student got a RC circuit with a voltage, with a step voltage up and down, you could solve that problem. Why can't you here? In the RC circuit, you would have, what you do have? You would have a C dVdt, which is like the first term, and then you would have a V minus R, V minus the applied voltage divided by R, which is like the second term. So if you can solve that equation, there's no excuse why you cannot solve this equation. Exactly the same equation here. So just think about in terms of series connected RC circuits. When you're solving this problem, you'll be fine. Very briefly then, where had you been? There's this band diagrams, drawing band diagrams in equilibrium. That is something we have done repeatedly. Same rules. And this will be the same rules at the end of your career also, which is start drawing a Fermi level, put the bulk regions where this is supposed to be, continuity of the vacuum levels and all. That's the same rule. Always correct. Now, in terms of DC current calculation, if you do not have any heterobarrier discontinuity, most of the time this diffusion equation, minority carrier diffusion equation, those will be fine. Those will be fine. But if you have a discontinuity like metal to semiconductor or between two different types of semiconductor, right? Like in lasers and others, use thermionic emission theory. No rocket science here, very simple. And you use that. Many times if you have like HBT where both diffusion and thermionic emission are important in different regions, you may have to put them in series, and whichever is the limiting current, that will govern the whole current through the structure. Small signal, again, you have to make a diffusion capacitance, a junction capacitance, and you calculate from the majority and the minority carriers. All of them exactly the same thing. But you realize in a MOS capacitance there were some spatial features because the oxides essentially prevented the electrons from flowing out. As a result, there are some, what was this? This is small signal, low frequency, there was high frequency response, right? And then there was deep depletion, right? Those things wouldn't have happened in a diode. That happens because you have a oxide region preventing the flow of the minority carriers to the other side. So you will study that a little bit deeply, right? And the large signal, most of the time, use charge control. For that, you'll get a zeroth order answer, more or less immediately. Don't have to worry about it. You always have numerical simulation, but first do a few lines in the back of the envelope 2 pages, I get an idea that what the solution should look like, then go ahead and fire it up in the NanoHub or in other places and solve the problem. Because without the 2 pages, you will not even know whether what's coming out of the machine is correct, or you put a wrong input parameter. You're supposed to put 10. You put 100. It's the middle at 2 a.m. in the night, and you are trying to solve a problem. You put 100. You get a solution. You take it to your boss, and the boss says that you don't have to come from tomorrow because you essentially you have no idea that how much current can flow. He knows, because he is seeing the measurement every day. So he knows how much current can flow through the structure. And you, the sophisticated engineer, just brought him an answer which is not even in the ballpark. It's very important to get the ballpark numbers right. Now, very quickly, I think I'll probably need 5 extra minutes today. I'll go through about a few more extra things. So I started here. This is going forward, looking ahead. And we talked about bipolar and how the temperature increase in MOSFET, this has put each technology in jeopardy. And by now, you understand how that wedge-shaped bipolar transistor works, right? All of you do. That this is a metal semiconductor, metal type Schottky barrier transistors, and the real bipolar didn't come around until 1952-53, manufacture of it. Idea was in 1948. You now know what is this transistor called, the MOSFET. This is a FinFET type structure. Electron goes from the left pillar to the right, and this region, which is sort of L-shaped region that you see in the middle, is the gate. That's sort of modulating the electron flow from all 3 sides, right? So that's because of control of the short channel effect. Short channel effect is getting more and more difficult. So you know all those. Given what you know, the chances are high that this is not what you'll have to work with or have to finish your career with in the next few years, or next decade, 2 decades, something like this. And there are many things people are doing, spintronics, biosensor displays. Let me give you a little bit of context. So the microprocessors is sort of in that upper edge where, sorry, this didn't come out correctly, but on the very high performance, and you want to make the transistors as small as possible. And there have been a lot of work, right? Last 50 years. That's what we had been doing in electronics. But these days, most interesting or many interesting works are in the large area electronics, where the cost has to be very small, and at the same time, it has to be very large. In a rooftop, you cannot put a microprocessor and say that this is my photovoltaic cell. You have to put the whole rooftop. Now, if you are trying to buy the photovoltaic cell with a microprocessor price, then you are not going to put too many photovoltaics up there. Therefore, the fundamental change that is happening across the board is that the material, this crystalline material, the basic thing that I started this semester with, that is probably not going to survive. So we are talking about polysilicon transistors, we are talking about polymers for batteries and other things, we are talking about mesoporous type structures where it can hold a large amount of charge in a very small volume. And then there are various other types of materials. And there are a lot of work in this field in terms of flexible electronics, energy and biosensing, lot of work. Now, what I'm trying to tell you, what you have learned, this is sufficient to understand any of this. If you just don't get afraid and spend just a minute about thinking about the fundamentals, all of them are essentially very, very simple things. Let me explain. This is, for example, somebody says that I'm doing organic electronics. Now, he shows you this device. This is how organic electronics are made, where you have a substrate. Do you see where the gate is? It's upside down. Gate is on the bottom. Gate is on the bottom. Then you have a gate insulator. That's also on the bottom. That's the green. And the thin film semiconductors, which is the yellow, which is in the top. And the source and drain are on the left and right. So it's an upside down MOSFET. That's what thin film transistors are. Why is it upside down? Because organics cannot stand high temperature. So you cannot put organics first, substrate first, and then start putting the oxide. If you put the oxide, everything will go away. So you put it upside down. But why do you care? Metal, semiconductor, metal. It's a Schottky barrier transistor. Draw a Schottky barrier band diagram. Do a Schottky barrier current flow through this structure. You are done. So it is nothing new. It's just a different configuration. You know, if I took a MOSFET, took my computer and flipped it around, the physics of the MOSFET doesn't change, right? Why would it change here? It's the same thing. But the material is very different. There are lots of random materials like pentasane, and the transport physics, the mobility, effective density of state, the effective masses, those are different. Those are definitely different. And this is something that Sony has come out recently with a display essentially based on very similar structure. And I'll ask you to do this, that even if I give you in the exam, which I may not, you shouldn't be worried. You should be able to draw a band diagram. You should be able to say what transport theory to use. It's a metal, two metals and a semiconductor inside. What transport theory do you use? Thermionic emission, right? Essentially, in the middle, use the thermionic emission on the side. And if you would you be able to use a numerical simulator in NanoHub? Of course, you should be able to use the same MOSFET. Just set it up with the proper value of mobility, effective density of state, and all. You should be fine. So this is something that is not something that should throw you off. Of course, the whole research is getting the right material that has a good mobility. Another thing is solar cells. Again, no problem, because the solar cells is a PN junction diode. If you take a PN junction diode and then shine light on it, then you have, what do you have? Shockley-Rittal generation, right? You have a generation. And if you have generation, the electric field essentially pulls the electron and hole out. And they pull the electron and hole out in through the respective contacts, you get current. If you know how to solve the reverse biased PN junction diode, then you shouldn't be worried about solar cells at all. Solar cells, then essentially, this is the electron hole pair coming out, and then they fall through, this is the band diagram, they fall through these two materials and the electrons are separated out. So this is not a big problem also in terms of what you know, you should be able to handle this. Now many times what happens is the electron and the hole, a lot of them recombine before they get out, so you cannot collect every photon that is coming in, and so many times what people do, they'll use the mixed structure. The two things sort of interpenetrate. Still a PN junction, but not the nice flat PN junction that I drew in the class. But you shouldn't care about that either. I mean, many times they do PN junctions like this, because what it allows you to do, it allows you to reach the junction very quickly and then separate out the electron and hole. This is a simulation of the materials, but it's again a PN junction. It's just that this is the N, this is the P, and it looks different, looks horrible, but it is a PN junction. How difficult can it be? And then you correspondingly solve your minority carrier transport equation across a junction, and that's about it. That's essentially about it. You put the two mirrors and the two contacts in, you have the solar cell. So what I'm trying to tell you that these things are very, very simple. What you have learned so far, if you just don't get afraid and sit down, say, okay, this is my device and this is two pieces of white paper. What did I learn in 606? Let me apply it. You will be ahead of most people in the field. One final thing is about biosensing. Again, a pure, and in fact I gave this problem in one of the final exams some time ago, and in which biosensing is here you have a XY grid of materials and XY grid of sensors. So every little square you see is the sensor. You have many of them. You can have, let's say, 10,000 of them, right? Now, each pixel in the sensor is decorated with a DNA molecule. DNA has a certain amount of charge. Now, let's say you have an unidentified molecule in the solution. So you have decorated all the with a known strands. Every pixel you have decorated with a known strand. Then you throw in the unknown. If you throw in the unknown, then the unknown is essentially going to bind wherever it finds its conjugate, because DNA binding is very specific, that it only binds with if it has a conjugate. And in that case, so I'm not going into the details of it, but the main point I wanted to make is that once you know, let's say this 3 red has lighted up, therefore the 3 reds have found its conjugate, but you already knew what the 3 points or the 3 pixels, what the original one was like, or because you put it there. And so thereby you can find out what the unknown is, identify what the unknown is, right? Somebody comes to your office and says that I have this new device, I want to analyze it. What are you going to do? You said no problem. Again, because this is a MOSFET. Current going from the green source to the green drain, and you see this is a thin film transistor, it's upside down MOSFET, right? Gate is on the bottom in the deep blue, and you have the oxide and you have the current flow, and when this charge, this molecule has a certain amount of charge, when the charge sits on the gate, so instead of applying a gate bias, you are just putting a charge on. If you put a charge on, can you not calculate surface band bending? Of course you can calculate, right? If you have a charge, the surface must be, will provide you compensating charge. And therefore you can see the band bending. The higher the band bending, it says that more charges have come at that point. That means conjugation has occurred. This is as simple as this. There is nothing more. And if you know the MOSFET physics, this is essentially, I would say, 2 hours of work to find out how current should flow in such a structure. And this is something you can easily calculate, that once the molecules sit in here, the change in the conductance due to surface band bending, you should be able to calculate. Now let me finally conclude on this, about this vision. And many times people actually historically try to work on this robot, that more and more sophisticated electronics. And that is what electronics people thought for last 50 years, that is why the electronics is going to go. There is a rapid shift. And the rapid shift is because that type of robot-based future requires too many resources, too many precious molecules, too much heat, too much energy. And it requires too much energy. The function is limited. It can do a few things. It can bring you a cup of coffee in the morning, but not really too much more. And it's not very reusable. But on the other side, many simple devices, these are processed at very low temperature, right? You hatch an egg at almost close to room temperature, no 1100 degrees Celsius required. And still, the functions it can perform, the near equilibrium, the structures, like this can catch, this is a jellyfish, it can catch its molecules. So you can again do the diffusion equation to see how the molecules essentially catches food, and then how it redistributes food, diffusion equation, carrier transport, essentially. You can analyze the whole thing, and it does amazing amount of things. So what I'm trying to tell you is the vision for the future is rapidly changing towards this more energy efficient, amorphous, diffusion dominated, close to equilibrium things, because that has to be the future of electronics. And so this is how I think that over your career, how this is going to change. But many of the things that you have learned in this course will remain essentially completely unchanged. Right? So that's something you should think about. So let me summarize. So I said electronics will continue to remain vibrant. That will hopefully good, because then that gives you a job. But I have a feeling that this computing and communication, that will get more specialized and out of the hand of device physicists. Circuits, communication, there will be a lot of beautiful work. But for device physicists, we have changed many times. It was started with electrical machines, branched into communication and computing, and it's going to change in energy conversion and healthcare and this type of other applications, because electronics always solved a problem of the society. It has to, right? Devices have to do something that solves a big problem. And the big problem is no longer being able to talk to your friends 2 hours more for no price. I mean, these days it's so inexpensive communication that there are other areas where electronics must branch. They give you a free cell phone. It is so inexpensive these days. Therefore, in order to make money, you have to go somewhere else. Okay, Let me end with a few acknowledgements. One is this Muhammad Assaman. He helped me with many figures, drawing many figures. You may have seen from time to time notes that Asad, we need to redraw this figure, which says that he helped me with many figures. Joe Psychos sitting in the back. This is 40 lectures in the 7:30 in the morning. It's not easy, so thank you. These are resources and for various supports for this videotaping, as well as for the teaching assistants and others. I often discuss things with Professor Mark Lundstrom. For HBT, I took many slides from him and Professor Supriya Datta. We work closely. And previous ECE606 classes, who, if you can believe it, I just used to write it on the board, and whatever they could take down, that is what it is. So at least now you can go back and listen to the lecture one more time. So that hopefully is much easier. And thank you all for coming to the 7:30 morning class. Okay, thank you very much. Things are not going to change, but as we go for new devices, how we apply them, apply the basic concepts, that probably requires a good understanding of what we have learned. And finally, I'll conclude. Now, if you remember, in the beginning of the semester, when I introduced 606, I said that we learned something about the foundation of physics, which is on quantum mechanics and statistical mechanics. And they will lead to the transport equation, the drift diffusion equation, the thermionic emission equation, and all those. And that would lead to a understanding of registers, where sometimes you have seen we have shine light on it, we have put various boundary conditions and applied battery across it. We have done all sorts of things. And we have talked about diode, minority carrier transport, bipolar junction transistor, various non-linearity or non-ideal effects associated with it. And finally, for last 10 lectures or so, we had been talking about MOSFET and MOSFET.
Nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
We'll be reviewing what we have learned very briefly. I have just picked up a few slides from before that summarizes or that highlights the important problems from before, and also probably a personal perspective that what I see ahead going forward. Now, let me begin by a quick review of what we have learned. We have learned many things, but the essence of what we have learned is not really too many. I'll talk about that. Going forward, many of the things that we have learned, the principles will remain the same. The MOSFET, the bipolar, the diodes, quantum mechanics, statistical mechanics, the basic for any other. And finally, the circuits and systems. That is, of course, a combination of all those things together that we haven't discussed. And 606 was this part. So what is it in this part that you should remember in general? Well, the thing that you need to remember is that how we arrived at the transport equation and what were the essential, and the transport equations always are so complicated. Remember, three-dimensional equation, partial differential equation of the diffusion, drift, and all those electron holes going through, that many times you can solve them numerically, no problem. And you have done that, right? You have done that in homework. But many times simplifications are necessary. And what I've tried to do throughout the course to explain the various simplifications that goes with registers, diode, and bipolars. You have learned about that. So what is it from this quantum mechanics, statistical mechanics to devices that we tried to understand? The thing was that in the beginning, the entire quantum mechanics, idea of the quantum mechanics was encapsulated in the idea of an effective mass, that there were periodic potential. I'll come to that. And when you solve the Schrodinger equation in the periodic potential, we got the band diagram, the EK diagram. And from the EK diagram, we argued that electrons mostly sit near the bottom. And when they sit near the bottom, then the curvature of how they move can be described by something called an effective mass. And that also gave us this idea about this band gap, the separation between conduction and valence band, the highest occupied level and the lowest unoccupied, highest occupied level and lowest unoccupied level. And so those two were from quantum mechanics. What did we learn from statistical mechanics? Well, Fermi function. That's the only thing we got from the statistical mechanics, and that we derived in equilibrium. And we combined these two ideas, the two notions, into this effective parameters. One was this capacitors. And I said what we didn't discuss, or would be discussing in this course, are that eventual applications of these devices in variety of configurations. For example, laser is just a diode, but we didn't discuss it, but essentially it's just a diode. Thin film transistor, I will talk a little bit about that today. It's a MOSFET. It's a pure simple MOSFET. If somebody says I have a thin film circuit, you shouldn't be worried. You should just say, okay, I know this is a MOSFET. I'll have to just do the square law, the channel length dependence and everything is exactly the same thing. MEMS is exactly again a MOSFET. MOSFET that has a variable, the gate capacitance is variable. Everything that you have done, in fact, that you can easily do the whole analysis. The MEMS analysis you can copy essentially line by line from the MOSFET analysis, almost, not everything. So the idea is that although we haven't discussed all the semi-classical devices for various applications, many of them, if you know these three, it's like an alphabet, then you can read or apply